the day of the exam. Okay, so MP stickers is due today, but let's cover some material. So, we were talking about the array implementation of lists, right? And we had specifically got onto resize strategy. And we had gone through the analysis of a resize strategy of if we're full, what do we do? If we're full, we will always copy to a new array and extend the size by 2, right? And we went through this by analyzing that in each round, how many copies had, and etc. And we ended up with that at the end, this has n squared plus 2n over 4 copies after n inserts. And I'm not going to cover the details of that again. You can rewatch from Friday. And then we also said that then we could generate because we don't really want the total number of copies, we want the number of copies per insert, right? And we said if there were n squared plus 2n all over 4 copies total for n inserts, we could say n squared plus 2n over 4 divided by n copies per insert, or big O of n. So if we choose a resize strategy of n of inserting 2 each time, it costs n time. So that means insert it back or insert it front is got a running time of n amortized. So what do we mean by amortized? This is the first new piece that I'm covering today. Because I didn't talk about it, I used the idea. Amortized says that instead of guaranteeing that the runtime of every step takes a certain amount of time, we are going to say that across n steps, it takes the amortized time times n steps. So this is a precise measurement. This isn't average or approximate, which has a sort of different meaning. Because if I told you the average runtime was 7, certainly over a large enough steps, that would, right, if the average runtime was n, over a large enough set of steps, we'd get n. But amortized says after n steps, we have n squared time. So it's a precise lower bound, not a approximation. But it doesn't say what an individual step takes. Okay. So let's try our other strategy. The other resize strategy we had was doubling. So in this case, if we run out of space and need more, we will double. So at the first time, we will make 1 copy, make the array from 1 to 2. The next time we will make 2 copies, make the array from 2 to 4. Then we will need 4 copies and make the array to 8, and 8 copies, right? So again, we're going to do this analysis by thinking of the rounds first. And so in this case, we are going to number the rounds starting at 0. So the 0th round, we make 1 copy, then 2, then 4, and then 8. So what is an expression that covers this? Ye, 2 to the r, not n, right? Because it's in rounds. 0, 1, 2, 3. So yes, 2 to the r. I like that. But, we're 2 to the rounds. We'll go over amortized again when we see it in this analysis. So, okay, 2 to the r copies per round. So again, we have our summation from k equals 0 to r of 2 to the k, right? So once again, we get a large thing, and we pull out our handy-dandy knowledge. Remember that this will be 2 times 2 to the r minus 1 plus 1. Okay. This looks much worse, doesn't it? It looks terrible. We had a squared this time, and we have an exponential. We had a squared last time, and we have an exponential this time. But again, we want to think of this in terms of copies per n. And I see someone has jumped ahead, and we can say that what? At a round, right, if we have done n things, we are what? 2 to the r is equal to n. So so r equals log n. And we plug this in, and we manage to get down to 2 to the n minus 1. Total copies. If we plug in log n and simplify, 2 times 2 to the log n minus 1 plus 1, 2 to the n. Total copies for n inserts. Okay. ln in classical math is specifically log base e, and this will be log 2, though you'll find that CS people are really sloppy and will write any log they want to mean. Okay. So, carrying this over, what do we got? We have 2 to the n minus 1 copies after n inserts. And we want to change this to, again, be copies per insert. And do we have a precise number of copies per insert? Well, on the first insert, we did 1 copy. On the second insert, we did 2 copies, 3 total. Well, this is looking bad. On the third insert, we did 0 copies. On the fourth insert, we did 4 copies. On the fifth insert, we did 0 copies. Sixth insert, we did 0 copies. Seventh insert, we did 0 copies. 8 insert, we did 8 copies. Well, our list, right, has things in it. If I did C, and then I copy C down, and then I do S, and I copy CS down, and then I do 2, and then I do 2, and then I copy CS 2, 2, then I do 5. So I've now inserted 5 times, right? The round is each time I have to do a copy. The insert is whenever I put something in the list, right? I'm adding to the back, then I do 225x. I've done another insert, but I have not made a copy, right? I haven't had to allocate a new buffer and make a copy. So, okay. So 2 minus 1 inserts after n inserts. Okay. So if I divide by n, I get 2 to the n minus 1 all over n is big O of 1. copies per insert. Amortized. Right? That's pretty huge. Because, so what is amortized? Amortized is saying that for any individual copy, we do in expectation that time. So you can think of it from a sort of probabilistic standpoint, but it's not quite that, because it also says that if we did n copies, we did the amortized cost times n explicitly, whereas probabilistic says in expectation we do that, but the actual number can vary. Well, all that varies in amortized is on the first insert, so insert 1, we could do 0 copies. Then insert 2, 1 copy. Insert 3, 0 copies. Right? Insert 4, 0 copies. Insert 5, we do 4 copies. Insert 6, we do 0. 7, we do 0. 8, we do 0. 9, we do 8. So every insert can have a very different, and after insert 17, we're going to do 16 copies, right, to be able to do insert 17. So the time it takes to run any individual step varies greatly. We did, right, we have list, pushback, C, S, insert 3, 1, 2, 3 is 0. Yes, 3 should be 2 copies, you're right. Or no, 3 should be 2 copies. Because we had to allocate a new array. A copy is, so we have an array of size 1. We can fit one thing in it, but you try and put the second thing in it. We allocate a new array and copy the old array to the new array. Right? Then, when it fills up, we allocate a new array that is twice as large and copy the old array to the new array. So the copies are copying from the old to the new. Right? To insert this 5, I had to copy my old array of 4 things into my new array of 8 things, and then insert the 5. Okay? Okay. So, if we do doubling, this is pretty efficient, right? Because our best running time for insert is constant, and we are adding constant overhead. So, running time for insert in array list with doubling is, or insert front, let's say, amortized. Okay. So that's pretty cool. We can have this contiguous array, And we can just keep inserting to it. And we have now a dynamic array, right? Instead of having an array be a fixed size, which is what we can do with new, we have a dynamic array. And in fact, this method is what is used under the hood in vector. Okay. So let's compare our two implementations. We have a singly linked list and we have an array list. Right? So if we use a singly linked list, well, let's walk through all of it. If we use a singly linked list, insert or remove at the front, it's easy, right? You just muck with the little pointers. It was head, temp equals new node, temp equals head, head equals temp. We're done, right? Order 1. There was a fixed set of instructions. Insert or remove at front with the array. Again, let's see. We just showed that memory allocation we can deal with. So we get, again, 01, but we have a star here, right? And the star here is that we're amortized. Okay. Insert at a given element. Well, let's be clear at what we mean by given. This is have a pointer. So, right, when we did insert with index, remember how we wrote that function index, right, that returned a pointer? Okay, let's talk about the amortized again, because we should get this down. I don't know the runtime for a single operation, but I know precisely the runtime for n operations. With average, I don't know this runtime for a single operation, but I have a guess at it. And for a large number, my guess becomes better. But in amortized, I know that if I do n operations from the start, it will take exactly n times the amortized runtime or less. I get a precise bound. Okay? Okay. Inserted a given element. So we have order n with a singly linked list, right? If you've got a pointer that you can muck with that points to the right place, I can think of constant. If I've already got index, if I already have index, if I went back and looked at my linked list code after I called index, what did I do? I went index, no temp equals new node equals index next. New node equals index. New node next equals index. God, I cannot say these things. I can write them. New node next equals index. Index equals new node. It looks like constant to me. I do 3 operations. Yes, but I'm saying we already have that pointer. You're absolutely right. The runtime of index is n. If I give you a pointer into the list, you don't have to... Well, because it turns out in many applications, this happens, that you will have a pointer into the list. So it's constant time. Okay. Now, with an array, we don't have to find the location, but what's the runtime to insert in the middle? We can play the amortized trick for allocating new memory if necessary. But is that enough? Yeah, I think it's order n. Why? What is making it order n? Right. With a with the case of a array, I have to have contiguous memory. So you could always be getting something in the middle. So I will right, with the front and the back, I could just do it, but I'm going to have to shift something. So order n. And I don't need amortized because the n subsumes that. Okay. Remove at a given element. So again, when we say given, we mean have pointer. With a linked list, we again get constant. And with remove, I now have a hole, and I have to shift the elements again. So order n. So in this funny case, a linked list has an advantage. That if I'm going to have pointers into my linked list can beat in this special case, which does come up. What about insert at an arbitrary location? No, and we'll go over the details of how we can do it. But the simple one was, imagine that we were inserting at the front, we fill our array backwards. So yeah, so this is order n, and it's because it has to do two things. It has to do find, which takes order n time, and insert takes constant time, so total is order n. Right? And with a array, we can do find how quickly. Well, we can do find in what time? How do I find the fourth element in an array? How much time does that take? Constant, right? It's just, square bracket. But we already knew that insert even with the pointer, so insert is n, so order n. Okay. So same thing applies here. And this version of the chart makes the linked list look really good, right? But if we want one last operation, if we want get data at, we want to get the data at a location index. Well, that's fine. So here it is order n, and here it is order 1. Right? So which is better? Well, depends. That having contiguous memory is really nice, but the running time for insert front depends on amortization, which could be a problem. But the linked list, it's more constants, but how often do you have a pointer into the middle of the list? So is this special case important to you or not? I don't know. Vector is this. STL list is that. Well, double E. The vector is a array list. Okay. So this is pretty cool. We have some nice data structure here. That is why we suggested it. It was not an attempt to trick you to suggest using vector. Um, insert at a given element assumes you have a pointer to that element, or a pointer to the pointer to that element. You don't have to find it. Insert at an arbitrary location or insert at an index. It ends up that there are, so the suggestion is if you have the data nicely sorted and you want to just access it, an array is ideal. That's certainly true that if your data is all organized from the data structures we've seen, the array provides the best access. If your only operation or your dominant operation is going to be to access data rather than to increase or shrink, an array is clearly a wonderful data structure. A linked list is more capable of handling dynamicism in contexts that an array cannot, which is why in operating systems it gets used down in the guts. Well, you might think runtime matters. The fact that insert and remove at front are constant is really important because I have possibly a fixed amount of time before I have to handle some piece of hardware. Whereas amortized across the long run time is fine, but if I have to get that packet off the network and I'm waiting as I'm doubling my array, that might take too much time. The other issue is that a linked list can cope with memory that is not contiguous. If I want an array a certain size, I have to have that much contiguous memory. And that, again, is not always possible in an operating system context. But as a user, in general, an array-based solution is going to be better for most cases. You would then get into questions of cache, which on modern hardware is really important. And you will see when you do 241, 240, or ECE 391, you will get some talk about how caching works. But what we want to do still today is talk about two really cool data structures an array is just a chunk of memory. A vector has methods on it and does things for you. A vector is an array implementation of the list abstract data type. Hash on the MP is a hash function that tries to summarize a larger data structure. Right. A vector is dynamic and resizable. An array, well, it's not immutable, but it is of fixed size. Immutable would mean you couldn't change the contents either. Yes, at this point, you probably never should use an array unless you are declaring a fixed size array. So, okay. But let's use this to build two cool data types. First, we have the queue. What is a queue? Well, it is like when waiting to get your COVID test. Here you are at the front, you get your little tube, and you're here going, yay, I get to spit in the tube, and I have a funnel or a straw. We can't tell at the moment. You have to queue in office hours. And I'm at the front, but perhaps you're back here. Someone else comes up to the queue, and they have to wait for everybody. So it is FIFO, people talk about, or first in, first out. Okay. How is it implemented? Well, we can implement it is has what? It has push back, pop front, which are usually called NQ and DQ. And what's the running time for these going to be? Well, if we use an array, constant. If we use a linked list, constant. Constant time. NQ and DQ. Awesome. We now have a data structure where all of the operations you can do on it are constant time. Add to Q. Remove from Q. So NQ is to add to the queue. DQ is to remove. And that's it. Well, let's see. Insert or remove at front, constant. Insert or remove it back is also constant. It's not an arbitrary location. It is a very specified location. We can insert at the front, remove it back in constant time with both versions. Okay? All constant. What about our next one, the stack? We've been using a stack everywhere. What's its order? Well, boxes and boxes and boxes and boxes, and you handle the top, right? So it is, instead of FIFO, abstract data type is ADT. LIFO, last in, first out. And we've been using this a lot. Right? We use this all the time. Anytime you make a function call, it's actually using this data structure. What are the pieces? We have push, add to stack, pop, remove. And this is much clearer, right? The stack is clearly constant time for both of them, right? Because there we didn't even have to hand wave that we could do front and back. Clearly, insert and remove at front, it works. So we now have two data structures that are constant time for all of their operations. Constant time for all their operations. Well, let's start walking through an implementation here. So if I showed you this Q header file, what can you tell me about it? What type of implementation is this of the Q? It's using an array list. So an array or an array list. And how is the data stored? Well, here's our key thing, is in an array. Pointed to, or let's say at, items. Right? It is templated, so we have these T's, right? And then we have two more variables. This particular implementation of Q, so not the Q abstract idea, this particular Q is being written using a C-style array. And I want to do this in part to defend how this kind of manipulation works. So if I was using a C-style array, a actual array, it's a C++ array, as opposed to a vector, how do I make this work? Because with the stack, right there, T star items is how we have defined that it's an array. Right? With an array, we would do something like equals new T say 10. Make our space for 10. Okay. Okay. But let's try and use it. And then we have capacity, which is max space, and size, which is currently number in Q. Okay. So, what I've got here is this chunk of memory that is items, and I want to try and work through the details of how to actually use this to show you that my argument that you can do this in constant time and still use all the space works. So let's see. So at the beginning, we're going to start out with capacity is 0, 1, 2, 3, 4. Sorry. 1, 2, 3, 4, 5, 6, 7, 8. Is 8, right? And our size is 0. And this is items. Right? Everybody happy with how the data structure is started and initialized? We've just run our default constructor, and we have created this chunk. Okay. So let's start in queuing. So the first thing we want to do, and we're going to assume the queue runs this way. So this is front and back. The first thing we're going to do is in queue 3. Okay. Well, I'm going to put that in the front, right? The queue can resize using the exact same resizing. When it is full, we will resize it. We'll talk about that. So we do in queue 3. And then size goes up by 1. Right? 8. How did I figure out where to put that? So in queue, right, looks like it is going to have, where do I in queue? I appear to be in queuing at items, square bracket, size. Everyone happy with that so far? And then we increase size. So this is my expression for where to in queue so far. I'm not sure this is the whole expression, but we do in queue 8, then we in queue 4. Okay. And then we dequeue. So in Q4, we're now size is 3. And now I want to DQ. Well, I DQ at the front, right? So I remove 3 and return it. So this is in Q at DQ at. So far, this is okay. Then I in Q at 7. Well, size is now 2. Huh. Item size doesn't seem to work. I better revise my in Q. Let's see. So what is the expression of where I should put 7? We have size. I'm going to write them bigger up here. Size equals, at the moment, 2. Capacity, and I'm going to write this short just to make it fit, is still 8. Items plus size. What's items? I did not move the elements over, because if I did that, I wouldn't have constant running time, would I? Capacity plus size? No. I think I need one more variable. I could, but if I move items over, that's going to cost a bunch of stuff. When you DQ, you return the element, or you don't. It depends. In our case, our DQ would be returning 3. So this is returns 3. But I think I need a front. So I'm going to have, again, unsigned front. So we DQ at front and then increase it. So we now have front. So now I have 3 variables. Start, front. I like front. So front is now at 1. So where do I NQ is now should be items front plus size. Okay, that seems to work, right? We decrease cap whenever we DQ. We move front whenever we DQ. We increase, or we don't decrease cap. Cap we just keep. Cap is not changing. We decrease size whenever we DQ. We, oh, you want to decrease cap? I'm not going to decrease cap. We'll figure out why. So, okay, then I in Q7. So 7 is going to go at 3, 0, 1, 2, 3. So that goes where it should. DQ, boom, boom. So that's taken, size is now 1. Front is now 3. I did the 2 DQs, right? So chunk, chunk, chunk. We're down to here. So now I in Q2. 1, 1, 3, 5. It's the memory allocation's there. We can only increase by 1 in small. So let's see. Now at this point we are at 5. Oh no, we filled up. We don't know where to put the next thing. But we DQ. Okay, so there's now 4 things in. So our size is 4. Our front is 0, 1, 2, 3. Oh, sorry, is 4. We have 4 things in, and our front is at 4. So far it works, but now we're going to NQ9. Huh. How do we NQ9? Modulo. Yeah. We want to do, instead of front plus size, we have a new expression, which is items front plus size modulo cap. So we NQ9 here. Does front work? Well, so then front is whenever we insert it front, increase front modulo size. We have a circular buffer. Yeah. This is a really useful tool. Okay. So we have this expression, and we have front is also going to be modulo. So we're going to keep front into size. Well, if I have more than 8 things, I'm going to have a problem. So let's look at that question. So now we have NQ'd some stuff. This is front. Size is 3. Right? And capacity is 8. Okay. So we do MON, D, we got the wrap, A, Y, I, S, DQ, we're still okay, H. Okay, so now we're down to here, right? These were all using the same thing. The DQ we saw, H we saw. So where are we at? Our capacity is 8. Our size is 8. And front is now pointing here. So 0, 1, 2, 3, 4, 5. So now we need to get bigger. Well, we know what to do, right? We're going to allocate a new buffer. This is going to have 16. Right? And then we copy it, right? So we change capacity will equal 16. Front equals 5. And size equals 9. Let's see. So we do A, Y, I, S, H, O, and D when we copy. Our size is 8, I guess. And now we do our insert. Oop. Yeah. So this copy method isn't going to work. We do need a copy, and they were exactly right. We want to change the front to 0 and copy it. So we want to copy this to here, and this chunk there. And then we want size to be 8 and front to be 0. And we're all done. So we copy from the front until it's all into the new one. And so we want, after we reallocate, front to be back to 0. And I have shown you how to get both a circular queue working and how to get constant time amortized with insert front. After the copy, you're going to set front to 0, and you're going to copy as if you were dequeuing, right? So you will copy going through and then copy it down. So you do the 8 copies from front rather than from the 0th index of the array. And yeah, it's just a for loop. Shouldn't you want everything after front to be at the end of capacity? So you're essentially doing a for loop of DQs, though you probably wouldn't implement it that way. I'm not sure I understand that. I'm going to. This is it for information, but I'll stick around for questions.